A database is a structured collection of data that's organized and accessed electronically, providing efficient mechanisms for data storage, retrieval, update, and management. Imagine trying to find a particular book in a massive library without any catalog. It would be a nightmare. Databases help us avoid that chaos by implementing systematic methods to organize data, making it easy to search and manipulate. Today, we're diving into understanding databases and data models, and we're making it as engaging as possible. So, let's get started with the basics. Databases, at their core, function like an organized filing system. Just like you wouldn't want your library to be a jumbled mess, a database ensures that everything is neatly arranged and readily accessible. Now, when we talk about data models, think of them as blueprints that define how data is stored and interacted with. This guides us on how to manage the data efficiently. All right, now let's consider some common types of databases. We've got relational databases, which store data in tables. Think of them like spreadsheets, where each row represents a record and each column represents an attribute of the record. Thoughtful pause. Then we have NoSQL databases, which are great for unstructured data, allowing for a bit more flexibility. For instance, if you picture a social media platform, its data might include user posts, comments, and likes, lots of varied information that doesn't fit neatly into a table. And to make things clearer, let's touch on a few important concepts. One key term is schema, which is essentially the structure that defines how data is organized within the database. It's like a map that guides you to find your way through your data landscape. Next, we have queries, which are requests made to the database to retrieve or manipulate data. Picture yourself asking a librarian for a specific book. You're querying the system. Finally, understanding normalization is crucial. It's like meticulously organizing your books to prevent overlapping categories and ensure that everything is stored properly. As we dive deeper, you'll see how these principles come to life in real applications, creating systems that are not just functional, but also elegant in their design. So, hang tight. There's so much to explore in the world of databases, and trust me, it's going to be fascinating. To grasp the concept of databases, let's start with the data model itself. Now, a data model, it's really a framework for defining how data is connected, stored, and accessed. Think of it like the blueprint for a building. Just as an architect creates plans to ensure a structure is sound and functional, a data model organizes how information interacts and fits together. So let's focus on three main types of data models: hierarchical, relational, and object-oriented. Now, as we flip over to relational databases, which is our primary focus, let's dive into SQL, the structured query language. This is the language that lets us interact with data in relational databases like Postgres. It's really exciting once you get the hang of it. Now check this out. SQL, or relational databases, take up 40.0, and that's visually emphasized on the chart. Meanwhile, the NoSQL family as a whole takes the cake with 60.0. Within the NoSQL segment, document databases form the largest slice, representing 25.0, followed by key value stores at 15.0. Then we see both column family and graph databases each making up 10.0. So what does this all tell us? Well, there are some clear patterns emerging. First off, relational databases still hold the title for the single largest individual category. But when we combine the NoSQL approaches, they collectively constitute a majority, right? This indicates a broad adoption of those schema-flexible and specialized stores. From this distribution, we can draw some practical conclusions for system design. If you need that strong structure, transactional integrity, and mature tooling, relational models are your go-to. But if flexible schemas and rapid iteration are key for your project, you might want to lean towards document stores. For ultra-fast lookups and caching, key value stores are a solid choice, while column family and graph databases are perfect for those niche workloads that benefit from wide column storage or traversing complex relationships. Overall, the chart highlights that modern architectures often balance the robustness of relational systems with the scalability and specialization offered by NoSQL, depending on the specific application requirements. Now, let's implement the following code that sets up our library database. First up, we're going to create a new database named library using the create database command. This action establishes a dedicated space to manage our book collection, which is super important, right? After that, we're going to utilize the \c library command to switch to the library database. This way, we ensure that any subsequent operations are performed within this context without any hiccups. Next, let's create a table named Books. This is where we'll store essential details about each book. The table is defined with 4 columns: ID, title, author, and published year. Now, the ID column uses the serial data type, which automatically generates a unique identifier for each book, making it super easy to track records. The title and author columns are defined as varchar 100, allowing for text entries with a maximum length of 100 characters. Finally, the published year column is designated as an int, enabling us to store the publication year in integer format. And there you have it. This foundational setup provides the structure necessary for our relational database, ensuring efficient data management and retrieval. Pretty neat, huh? Sure. Let's dive right in and see how we can implement a categories table to enhance our book database. We start by creating the categories table using the create table command. This command defines a new table with 2 columns: an ID column, which we designate as the primary key, and it auto-generates unique identifiers for each entry, and a category name column, where we'll store the names of each category. This setup ensures that each category is distinct and easily referenced. Next, we need to establish a connection between our books table and our new categories table. We can do this using the alter table command, which allows us to modify the existing structure of the books table. Here, we'll add a new column called Category ID, which will serve as a foreign key linking back to the ID column in the Categories table. By doing so, we define a many-to-one relationship, meaning that each book can belong to one category, while a single category can encompass multiple books. This arrangement is essential for organizing our data while maintaining relational integrity within our database. Now that we've established our foundational tables, it's time to dive into data manipulation and add some essential information to our library database. First up, we're going to insert 3 book categories: fiction, science fiction, and nonfiction, into the categories table. This step is crucial because it helps us effectively categorize our books, providing a structured approach to managing different genres. Next, we will populate the books table with 3 engaging titles: Dune by Frank Herbert, 1984 by George Orwell, and Sapiens by Yuval Noah Harari. Each book entry will include important details such as the title, author, published year, and, of course, a reference to the category it belongs to by way of category ID. This relationship ensures each book is neatly categorized, enhancing our database's organization. By executing these insert commands, we showcase the power and efficiency of SQL in managing and populating relational data, really enriching our library database with curated content. With these steps, we're not just adding data, we're laying down the foundation for meaningful queries and insights that can emerge from our library's inventory. It's all about creating that framework for deeper understanding. Now, let's see how we can retrieve data from our books table using SQL queries. So, the first command we're going to use selects all records from the table. This is indicated by the asterisk, which just means we're fetching every field from every row. It's the simplest way to get a broad overview of all the books stored in your library database. Now, if you're curious about specific information, like say we want to see only the titles and authors of books published after the year 2000, we can refine our query. By using the select statement, we can specify which fields we're interested in. So here, that would be title and author. Then, the where clause comes into play, allowing us to set a condition for our results. This way, only the books that meet our criteria will be displayed. It's really cool how SQL empowers us to filter and retrieve targeted information efficiently, tailoring our data retrieval to suit our needs. So, whether you're browsing through a few titles or looking for specific authors, SQL makes it all possible. Now, let's see how we can join our books and categories tables to retrieve some meaningful information. So the first part of our SQL statement is going to specify the fields we want to display. We're looking for the title of the books from the books table, and then we want the category name from the categories table. Next, we define which tables we're querying from, starting with, the books table. Now, to connect the two tables, we implement the join clause. This is where the magic happens. We use the on keyword to say that the category ID from the books table should match the ID in the categories table. This relationship allows us to seamlessly combine the data, creating a comprehensive view of book titles alongside their category names. So, when we run our query, we get a well-organized list that not only tells us what each book is, but also categorizes them. Isn't that neat? This way, we really emphasize the interconnected nature of the data we're working with. Joining these tables enhances our ability to query data meaningfully, reflecting real-world relationships within our database. It's pretty powerful, right? Now, let's see how we can enforce data integrity in our books table. To ensure that every book has a title, we begin by applying a not null constraint to the title column. This means that no record in the books table can have a null value for the title. Each book must have a designated name, which is crucial for identifying it in the library. Next, we want to validate the published year entries to confirm that they are all positive integers. We accomplish this by adding a check constraint named valid year that specifies the condition must be greater than 0. This guards against erroneous data entry, such as including books without valid published years or, heaven forbid, negative values. By implementing these constraints, we enhance the reliability and accuracy of our database. This not only helps maintain a well-structured and trustworthy dataset, but also facilitates smoother querying and reporting in the future, ensuring users can rely on the data's integrity in all operations. Now, let's dive into how we can analyze the distribution of books across different categories within our library database. We're going to implement an SQL query that fetches the names of categories along with the count of books in each. By using the count function, we can effectively aggregate the number of books that belong to each category. Now, to make sure we have a comprehensive view, we'll employ a left join between the categories and books tables. This approach guarantees that we retrieve all categories, even those without any associated books, ensuring we don't miss out on any valuable information. After that, the Group By clause will come into play, which groups our results by category names, enabling the count function to accurately tally the number of books in each category. This powerful combination of aggregate functions and joins is really fundamental for pulling insights from our data. It clearly demonstrates how we can uncover meaningful relationships from pieces of information that might seem isolated at first. So, by executing this query, we're not just deepening our understanding of category distributions, we're also showcasing the robustness of PostgreSQL's analytical capabilities in generating insights from data stored in relational databases. We've traversed various aspects of databases and data models, establishing a solid foundation of understanding. Whether it's creating tables, inserting data, querying, applying constraints, or analyzing data, each component plays a vital role in the dynamic world of databases. Remember, the efficiency of data management translates into improvements in accessing information, enhancing decision-making, and leveraging analytics for data-driven strategies. As you progress on your journey of mastering SQL and PostgreSQL, practice remains key. So, experiment with what you've learned here. Play around with queries and tables, and most importantly, always keep in mind the potential your newfound skills can unlock. Thank you for joining me on this adventure into the world of databases. Keep coding, keep querying, and don't forget to look for those valuable insights in your data. Happy learning!